Right, so question 2, part A. Tin can for science experiment. Tin can has a diameter of 7.5 and a height of 10.5. That might be useful. We better write that down. So that's the height of the can. She drove a 9 centimetre long nail at an angle into the side of the can until it reached the bottom edge of the can. What angle does the nail make with the base of the can? So we're talking about that angle in there. What angle does it make with the base of the can? Now this sounds like a trig problem, and it also sounds like we might be needing so, ka and toa. So let's set ourselves up, help ourselves by putting in something that would be useful. So, ka and toa. Angles, you can call it x. I'll use the angle symbol of theta. Obviously there's a right angle in here. This would be the hypotenuse. This would be the adjacent side. And I'm trying to find theta. We won't use this one because we don't actually know the height that the nail goes in. That's the height of the whole can. So this is a cos problem, ka. For those of you that like using the triangle, you can find the ka triangle. Adjacent side 7.5. Just check they're in the same units. They're both in centimetres. Hypotenuse. And we want the cos theta. So one line of working, cos of theta equals ka a divided by h. Theta equals cosine to the minus 1. And working that out on the calculator, 33.6 degrees to 1 decimal place. Right. Now part B refers to the same diagram. How far from the top edge was the nail driven into the side of the can? How far from the top edge? So we're looking for that length there. I suggest we find the lower length first, which we can call x, and then we could subtract that from the 10.5 to find that height. So if we're finding x, we could use SOHCAHTOA again. We could in fact also use Pythagoras' theorem because we've got two sides and we want to find the third. The third side is a short side. We've got the hypotenuse. So if I'm using Pythagoras' theorem, and I'll just write my answer here, x would equal the square root of the longest side squared minus the other short side, because I'm looking for a short side. And when I look for a short side, Pythagoras' theorem, it needs subtraction. Alright, remembering to use brackets around that on the calculator, we get a value of 5. Or 4.97, perhaps we should, because we're part way through a problem, we'll use the whole decimal. 4.9749 ... So therefore, the height that the nail would be driven in is going to be 10.5 minus 4.9. And perhaps using answer on the calculator, 10.5 minus your answer gives me 5.5 centimetres to 1 decimal place. And you should write that working down below if you haven't done it. Right, part B. Now this is clearly going to be our bearings question. So reminding ourselves about bearings, clockwise from north, and we should have 3 digits. So now we'll read the information. The boat leaves D and travels for 7 kilometres at a bearing of 50 degrees. So clockwise from north, that angle in there must be 50 degrees to the point E. The boat then makes a turn to the right through 90, travels to F, down that way. Point F is 10 kilometres from the initial point D. Well, I can see that. Find the distance the boat travels on leg EF, so we're looking for that length there. Clearly this would be a good opportunity to use Pythagoras' theorem again. X, or the length EF, is going to equal the square root of, there's the hypotenuse, 10 squared, and because once again we're looking for a short side, we should use subtraction. 7 squared. And we get 7.14 to 2 decimal places. Right, now the next part of the question, of course, is going to rely on this diagram, so I may have to leave the diagram there. Part 2 says to find the bearing of D from F. So we want for part 2 the bearing of D from F. Now the important thing is the from, so that's where I'm standing here. I'll just draw in a north arrow. I'll just erase the X to stop the confusion. And we want the bearing of D. So I'm going to have to turn myself all the way around to find the bearing of D out this way. So it's that bearing I want there. Obviously 180 for half the circle, perhaps another 90 and then a little bit. There are lots of ways to do it. I think perhaps if we could find this angle and this angle, we could subtract both of those from 360. Let's start with this angle in here, we'll call it theta. I've got two sides, I've got the hypotenuse, and if that's the angle, this would be the opposite side, so it becomes a SOH problem, sine. Now I haven't got a lot of room here, so if we quickly write a SOH triangle, opposite of 7, hypotenuse is 10, oops, and I want the sine of theta. Of course you'll need to set out some nice working. Theta is going to be sine to the minus 1. Working that out on the calculator. 44.427, and we'll keep the extra decimals. So that gives me theta. We could also work out this one once we know theta using angles in a triangle if we wanted to. I actually found with this one, if you put in this arrow, using alternate angles is often useful for a bearings problem. So that would be 50 using alternate angles. Because this whole angle is 90, that would make that piece 40. And so once again using alternate angles, that piece in there would be 40. So now I've got that whole lot. So to find the bearing, and I'm squeezing it in, obviously you would write it down below, the bearing would equal 360 minus 40 minus theta, and the answer to theta is down there. So working all that out on a calculator, we end up with 275.6 degrees to 1 decimal place. You might like to round it to 276 to 3 significant figures. So just check the working on that one. There are other ways to do it. Right, the next one has a Ferris wheel, and once again it seems to imply circle geometry, but we'll just have a quick read. Radius of 10, turn through an angle of 150. How far above the base is she? So we want to know that height. How far above the base is she? Look for a right angle triangle, so we could if we put a line through here, that will give me a right angle triangle. We want this height here. Now, do we know any other angles in this right angle triangle, this piece up here? Of course, if that's 150, we've got 90 to here, so this angle would be 60 degrees. And perhaps if we just draw that out here a little bit bigger, I've got 10, I've got 60, and I want to know this height here. Of course, once I've got this height, I can just add on 10 meters for that height. So we're going to add the two heights together. X plus 10 will give me her total height. Step 1, label the sides, hypotenuse, opposite, It's the sine, for those of us that like using triangles. Opposite, hypotenuse, sine of 60. Nice line of working. 10 times sine 60. 8.66, and there's more to come. And therefore the height we know is going to be 10 plus x. So adding 10 onto the number in your calculator, we end up with 18.66, and that would be metres to 2 decimal places, which looks about right. Right, last part of this question, quite a hard one. Let's see what we can do with it. A has the coordinate 0, 6. B has coordinates 3, 0. I know about graphs and coordinates. That means that height is 6. This distance is 3. Perhaps it would be more helpful if we wrote the 6 and the 3 there. Calculate the shortest distance from the line AB to the point C. So shortest distances should be, if you think about it, at right angles. You think about that. If I try and draw any other line from C out to there, they'll all be longer than that. The shortest one would be the one at right angles to line AB. So if we clear all those away and just draw in this one at right angles. So I need to find the length of that line. Now finding lengths, Pythagoras or trig. So let's write that down and think about it. To be able to use Pythagoras, I need 2 sides and I need 1 more. And to use trig, I need an angle. There's one angle down here of 90. I wonder if we could find that angle. If we go back to our original big triangle here, we could begin to find this angle in here, because I've got an opposite side and an adjacent side for this one using the big triangle. So it's a tan problem. For those of you that like using the triangles, the opposite side is 6, adjacent is 3, tan of, now we need to call it something, let's use theta. So nice working, tan of theta, 6 over 3. Theta will be 10 to the minus 1, which gives me an angle of 63.44, and there's more to come, so we'll leave it there. Right, now if we revert back to the small triangle, so just see if I can rub out the highlighting, and we go back to the small triangle here, I've got 3, I've worked out theta, theta is about 63, so now I should be able to find x because I've got a side and an angle and I want another side. For this triangle, this side becomes the hypotenuse of this triangle and this side is the opposite. So I need a sine, it's a sine problem. And if you like using the triangle, let's fill it in. The opposite side is x, hypotenuse is 3, sine of 63 point, and we'll use some more of it. So nice line of working, 3 times sine 63.4, etc. So if we're working that on the calculator, we could do sine of answer times 3, 2.68. There's no clear units, so we'll just write units, and that's rounded to 2 decimal places. So that should be the shortest distance.